The reason why we're interested is because in industrial hygiene, we're trying to protect workers. It might be office workers, they might be, or it might be residences, they might be industrial sites, might be manufacturing, and so on and so forth. Might be people on space shuttle, for instance, in confined space. That is the nature of the space shuttle. So we're always looking at environmental systems in one form or another. Today, we're going to discuss a specific kind of ventilation system, a capture ventilation system or exhaust ventilation. We're going to learn some basic principles about measuring how effective these systems are, about measuring flow in ductwork, measuring whether or not a device is capturing contaminants or not capturing contaminants, where it would be exhausting and so on. We're going to learn about how to take those measurements, what instruments are involved in taking those measurements. The same instruments that we're going to be talking about today when we're talking about capture ventilation or exhaust ventilation are going to be the instruments that are going to wind up being used to some degree in indoor air quality and other systems where we're dealing with recirculating air systems or fresh air systems. Any of you guys, have any of you guys taken industrial ventilation, that course? Any, you plan on taking it? Anybody, you going to take it? Okay, good. So when do you plan, you going to take it next semester? Oh, okay, good. Who's Brian's like teaching it, I guess, right? Okay, good. All right, so this is kind of an introduction into that.
Industrial ventilation.
Yeah, industrial ventilation, right. Well, you're about to learn what that really means. Okay, just for starters, just the basic characteristics of air. Why are we interested in this? Because moving air is work. To get air, go from one place to another, you have to do work. So typically the way that we do that is we use a fan or a device to move air. That device, what it's actually doing is it's creating a pressure difference between one spot and another spot. So when you have a fan like the one we have over here, the exhaust fan out of my basement, when you have that fan, you know that on one side of it, it's sucking air in. It has negative pressure on one side. It has positive pressure on the other side because it's blowing air out. That negative pressure is basically a kind of potential energy. In order to get air to move, you have to have a difference in pressure. So if we connect that to ductwork, we can run that ductwork to another area. And since that we have a negative pressure at that point, that negative pressure can induce airflow through that ductwork. So some of that negative pressure becomes converted to kinetic energy or to do actual movement of the air. When the air is moving, the speed that it's moving at, the amount of air that we're moving, that has to do with how much work that we're doing, how much energy we're expending, how much work we're doing. That has to do with the density of the air. It has to do with the velocity, the size of the ductwork, the frictional forces, heat, and so on and so forth that's generated in the process. So all of that kind of ties in. When you take that full industrial ventilation course, you really take a close look at all the formulas that are involved in calculating all this stuff. You're interested in the density of air. That's the density of air here at sea level, right, in New York City. Density of air in Denver, where it's a mile high, they call it a mile high city, where it's like 5,000 feet or 6,000 feet above sea level, density of air is different there. So when you move air at the same velocity, you're doing less work because you're not moving the same amount of mass, right? So there are situations where you're actually interested in the density of air. Now, the composition of air, the molecular weight is 29. That's how do we know the molecular weight is 29? I mean, why should that be obvious to us? What is air mostly made up of? There's some oxygen in there, right? But only 20%. It's mostly nitrogen, right? The molecular weight of nitrogen is 14, right? So it's N2 usually, it's found as N2, so that's 28. So the average molecular weight, so the average molecular weight of air based on the components of it is about 29, right? So we know that that's basically what's going on there. And if we want to understand how much mass there is in a certain volume of air, we know we have conversions for that. For instance, we know that we can convert, knowing the molecular weight, we know that 1 mole, 1 molecular weight in grams takes up 22.4 liters of space. So we can convert between volume and the weight or the mass of the air that we're dealing with. In fact, when you get into it, what's that?
4.45.
20, yeah, exactly. 22.45 liters of air in the molecular weight in grams. In other words, 29 grams of air takes up that much space at standard temperature and pressure. When you get into industrial ventilation, you're not going to use that particular formula because almost all the measurements that you're going to work with in the United States are going to be in US units. So you're literally going to learn the conversion, not from grams, moles in grams to liters, but you're going to learn pound moles, how much space a pound mole of air. Like, in other words, 29 pounds of air takes up so much space. I don't remember it off the top of my head because I work a metric system usually, but if you're actually a person that works with industrial ventilation systems or with HVAC systems, if you're an engineer that designs air conditioning systems, you're working in cubic feet per minute. Feet per minute is the velocity. You're working in terms of volumes and conversions. You're talking about pound moles instead of gram moles, and so on and so forth. So you see what the composition is, and this will come up and this will make sense to you. For today, we're just getting a taste of this, so we're just going to assume everything we do from this point on is in standard temperature and pressure, and we're not going to worry about density or correcting the density or anything like that. So why do we need to move air around? Well, industrial hygiene, there's two reasons. One, if you're a mechanical engineer and you're part of the teams that's designing a building, you need to provide comfort, cooling, and heating for air spaces in that building, right? So you are designing the system to make it comfortable. In that building, if you're an industrial hygienist, your main reason for moving air around is to protect workers from hazardous materials that might be exposed to in the work site. Okay, so in either case, also in indoor air situations, there may be hazardous chemicals around. There may be comfort issues too, like buildup of odors and recirculated air all the time. In HVAC systems, air conditioning systems in buildings, the way that we control odors, way that we control hazardous materials or materials that might be of concern in an indoor environment is by dilution ventilation. So we're taking the air in this room is coming in through diffuser, that square thing up above us there, and it's being supplied into this air. There's probably another one back there somewhere, but there's probably a couple. So we have air coming in through diffusers into this room, and then it's going back up into the room either through those two panels at the back there. There's a space in the ceiling above the ceiling. The ceiling is actually, air is ducted to this supply diffuser. Air comes into the room. Now it's got to displace the air that's in here. So it's got to, we have to get rid of the air. So if this door is closed, where it goes up into those two diffusers, those two panels in the back, or grates in the back, where it can go up into the ceiling. And that ceiling is under negative pressure because it's on the other side of the fan that's supplying that diffuser. So literally air comes in here, goes out over there, goes back to the air conditioning unit, and is recirculated over and over and over again. What happens at the air conditioning unit? At the air conditioning unit, you have either a steam or a hot water coil to heat the air in the wintertime, or you have a freon or a chilled water coil to cool the air in the summertime, right? And sometimes you have both of them operating at the same time to balance the air. In other words, during the daytime, you might get cooling, and at night, you might get heating, and so on, right? And actually, sometimes they even have a coil that could be either hot water or cold water, depending on what they need at any particular time. So we'll talk a little bit about how those systems work, especially as we get into indoor air quality and how the design. We might even be able to arrange a visit. Usually it's hard to do at night, so I don't know about doing it at night, but we might be able to arrange a visit to see the mechanics of the HVAC system that operates this building, for instance. So we'll see if we can arrange that. Okay, so the reason why I brought this up is because this air is recirculated over and over again. So if we're using magic markers, if people are wearing perfume, if we're using if they're using cleaning chemicals, if we recirculate the air over and over again, over time, these contaminants are going to build up in the air, and we need to control them. Okay, and the way we do that in this kind of systems, we do it by dilution ventilation. Mainly what we do is we take a portion of that returning air and we dump it outside and replace it with fresh air from the outside. Or what we call, in New York, we call that outdoor air instead of fresh air. We don't see too much real fresh air here, right? And the idea there is The more exchange that we get with outside air, dumping stale air from here and pulling in fresh air, the more dilution of these contaminants that we manage to achieve. But why wouldn't we want to just do a lot of that? Why not just, exchange a lot of air? Why do we even limit it? Right? Anybody have a hazard guess on why we might even limit it? What's that?
We need to maintain the outdoor air quality as
Well,
well.
we need to maintain the temperature here. So if it's a dead of winter, it's 0 degrees outside, and we pull in a lot of fresh outside air, what's going to happen? We're going to be freezing here. We're going to be wearing our coats here, right? So in the summertime, we have the same issue where in the summertime, we have hot air outside. If we exchange a lot of cooled indoor air with hot outdoor air, it's difficult for the air conditioning system to keep up with that. In other words, you'd have to have a much bigger air conditioning system, and it's costing a lot more in energy. That became a big issue in the 70s because we had an oil crisis, energy prices skyrocketed in the 70s, and people started to design buildings that limited the amount of fresh outside air that you could get in a building. And eventually what happened is that those buildings that didn't have openable windows, that example, this building is like that had limited amount of ability to exchange air, indoor air with outside air, started to get a lot of complaints. In fact, so many complaints that there were an enormous amount of complaints, a lot of controversy about it, and you started to hear about this idea of sick building syndrome, where people would be so uncomfortable that they wouldn't want to work in the environment. At that time, we used to use building materials that would off-gas a lot of VOCs and materials, formaldehyde, glues with solvents, and so on and so forth, and carpeting. It wasn't unusual for me to walk into a building that had just been commissioned, just been finished, and people were moving into it, and you'd get new carpeting smell and paint smells in that building for weeks or even months after they opened the building, until that sort of tapered off. It has a half-life because this is all stuff that's evaporating from the building materials. Motorhomes or temporary homes, they have a lot of fiberboard in them, which has a lot of formaldehyde in them, insulation that can off-gas formaldehyde. So that became a big problem. In fact, the EPA opened an office building in Washington that after the first year they had to close and remove all the carpeting and replace all the carpeting because it kept off-gassing materials into the building that were, causing people to not want to work there. So dilution ventilation has its place, but you need enough of it to control the amount of material that's getting into the air. Now, how about smoking? Like people smoke and stuff like that. Can we control smoking, the contaminants introduced by smoking, by using dilution ventilation? Well, yeah, you can, right? You can moderate it. In other words, you can reduce the amount of smoke that's in the air, the odor from smoke, and so on, to some degree by dilution ventilation. But you're never going to be zero. You're always, anytime you use dilution ventilation, the contaminant has to get into the air first, get mixed into the air before you can exchange it with outside air and dilute it. So anytime you use dilution ventilation, you always have some kind of exposure. You can try and control it with dilution ventilation, but it's expensive and not, inefficient. Now, when we have a serious hazardous material, when we have a worker that is exposed to, say, toxic materials or materials that we're really concerned about, we don't want that getting into his working space, into his breathing space, because even if we dilute it, he's still getting a significant exposure. So what we use instead is we use local exhaust ventilation. We create an environment where the material that's getting into the air is captured before it gets into this breathing space, before it gets out into the room and needs to be moderated with dilution ventilation. Any of you guys work in a lab? What do you have in a lab that takes care of that for you? You have a lab hood, right? A lab hood is a perfect example of local exhaust ventilation. It has, you have an exhaust fan that runs continuously. Anything that's happening inside that hood is getting pulled away from the worker, away from the room. So it can't get into the room, can't expose the worker. It's completely captured, so you don't have that exposure. Depending how efficient the hood is, whether you maintain the hood is operating properly, if it's designed properly, that works great. That's what an industrial ventilation specialist does. He designs these systems so that he knows that there's sufficient exhaust there, sufficient velocity pulling this stuff away from the worker, that he doesn't have to worry about the worker getting exposed to it. Okay, but that's a whole area of study. You got to learn about it. You have a semester of it. You can learn quite a bit about that. In fact, it's a good step towards becoming the kind of person that can design these systems, and not only design these systems, but also troubleshoot them. Lab hoods, medical hoods, and so on and so forth. They have to be calibrated. They have to be tested, calibrated annually, sometimes depending on the material they work with, even more frequently than annually. Some of them have specialized functionality because of the types of materials that you're working with. So there are specialists that actually go in to test these, certify them, and make sure that they really are protecting the workers. Almost all of them have to be done at least once a year, many of them even more frequently than that. Okay, so why do you want to use local, when do you use local exhaust ventilation? When you're using something toxic, when you're using a material that's really dangerous to the worker, you don't want any of it getting into his breathing area. Strong odors, irritating materials, flammable liquids, you want to control them so they can get into the room and get to the point where they can burst into flame or explode, where you have high emission rates of toxic materials, and where the other ways of controlling it aren't applicable, like dilution ventilation. Okay, of course, first thing you want to do is try and substitute or eliminate it, but when you can't, that's when you get into local exhaust ventilation. Okay, so here's a few operations where you might use local exhaust ventilation. Spray painting, for instance, spray booths. If you have ever seen a professional automobile body shop where they do a lot of spray painting of vehicles, they have spray booths. And these spray booths have filtration. They have like enormous walls of filters on them with fans behind them, continuously pulling air so that the worker can spray the paint onto the car and have all of the fumes and the material from the paint pulled away from him. On the other side has an enormous wall of filters. So the fresh air coming in is filtered before it gets into that space. Why did they filter it before? Why did they just use outside air? Why did they filter it before? What do you not want on that car's finish? You don't want dust and dirt and stuff, right? It's got to be clean air, right? So they have enormous filter banks on one side, and then they have another set of filter banks on the other side, which is intended to capture any particulate material before it gets outside. You don't want to have that stuff come out your exhaust vent and then spray onto your neighbor's window or something like that. So you have them on both sides. So you have spray painting operations, grinding operations. In other words, a guy that's grinding mortar or something like that between the bricks on buildings. You don't want him being exposed to all that silica and dust and caustic dust from the cement or the mortar that's between them. So those grinding devices now have hoods on them, hoods on the machines themselves, on the devices that they use to grind them, brushing and polishing operations, metal cleaning, plating. Those are all, they have hot baths. Some of them have solvents in them that you want to control. Laboratory work. Yes.
So the hood captures the particle.
Exactly. The hood captures all of the material, or as much of the material as possible, so it doesn't get into the space and doesn't get into the breathing zone of the worker. Woodworking. Anybody here do any woodworking? Nowadays, if you buy a table saw, if you buy a decent table saw nowadays, you'll notice that almost all high-end table saws now come with connections for duct work, so that you can connect it to an exhaust ventilation system. So as you're sawing wood in a table saw, the saw desk gets captured by the hood that's surrounding the blade, and it gets pulled in and sent out through a filter and captured, so you don't get sawdust all over the shop. That reduces the fire hazard. It reduces the exposure, the worker's exposure to sawdust in the air, small particles of sawdust in the air, and so on. Capture ventilation. You guys notice also that they also nowadays have a table saws that have a capacitive system, that if anything conductive touches the blade, it stops instantly. You guys ever seen that? They do a demonstration with a hot deck and it saves fingers. In other words, literally, if you're pushing wood through the blade, if your finger touches the blade, it stops instantly. They actually, I have to show you this since you guys haven't seen this. See if I can come up with one of these.
It's like an emergency stop.
Yes, exactly. They have a couple of demos that they show with hot dogs.
The Grommet has gifts for all the wonderfully one-of-a-kind people
Everything's
in
got
your
an ad
life.
on it
Each
nowadays.
weekday, we reveal innovative products. And if we can find amazing gifts they've never seen, imagine what we can find for you. Get free shipping.
This is my saw stop table saw. This is the heart of my workshop. 23 horsepower. And when I don't need it, brand in my shop because I love this. I feel safe around it. It doesn't change my shop is the reason dogs are actually terrible. I would slow motion camera.
Is that amazing?
All right, so let's take the blade and the brake out and see what happened. All right, so
It's actually got a
there it
brake in
is.
it. A little
There's the
spring-loaded
blade.
device that like it gets released and stops
and
the
there's the
blade
brake.
instantly.
It jams up
But you
on the
saw it.
blade.
If you look at the hot dog or somebody's
You
finger,
can see these holes
see
here.
like a little
What
scratch on
gives
it,
way,
right?
so the
Which
blade sticks
otherwise would have been a
into
lost
the brake.
finger or hand for that matter. What's that? Yeah. Who would do that? I'm sure there's some guys that test it with their own fingers, but hopefully there's a hot dog. But at any rate, okay, so they have these things. And the other thing is that table saw was no doubt equipped with a connection for a duct system, so you could pull the sawdust away down into the saw blade and away from the worker, so you didn't collect a lot of sawdust on it as well. Okay, ventilation systems. One of the things you want to learn how to do is, in addition to designing them, to actually learn how to evaluate and make sure that they're working correctly. And all this is done by understanding how air movement and air pressure are associated with each other. Okay, so there's two kinds of pressure that we're interested in. One of these is called static pressure, and the other one is called velocity pressure. If I blow up a balloon, actually in this room right now, we are sitting under a column of air, which is 50,000 feet tall. So the pressure on our bodies right now is 14.7 pounds per square inch, which I think is something like the equivalent of 32 feet of water, the equivalent pressure of 32 feet of water, or 29 point something millimeters of mercury, right? The equivalent weight to that. So there is that much pressure pressing against us right now. If I held up a gauge here, right, it would say 0, because the pressure on both sides, if there's two connections to it, pressure on both sides is the same, 14.7, 14. So it's reading 0 difference between those two pressures. We don't even sense that pressure because our bodies are used to it. We've lived in it forever, but we are under that amount of pressure all the time. Varies a little bit, when there's a high pressure system going through, we know by the way a barometer works, it's got mercury in it, and we know that it can support a taller column of mercury. So, it goes up to 30 inches of mercury, 30 millimeters of mercury. And when we got a low pressure system going through, the air pressure, that's based on the temperature of the air usually. Warm air is lighter, cold air is denser, right? So what happens is the pressure on our bodies varies. Not enough for us to feel it, but enough for us to measure it with a barometer. And we can predict weather that way, because a lot of times when a low pressure area, when warm air passes through, we know we get rain. When cold air passes through, after it goes through, we get clear weather and stuff like that. So you've seen these devices that predict fair and foul weather based on the motion of a barometer going up or down. So at any rate, that's called static pressure, right? It's pressing on us from all different angles. It's not moving. It's just there all the time. If I blow up a balloon, the static pressure inside that balloon, because it's under pressure from the balloon pressing in, is higher than it is outside. but it's not moving. It's all standing still. And anywhere in that balloon, the static pressure is equal throughout that balloon. On the other hand, if I'm standing here and the wind is blowing in my face, I can feel the pressure from that wind. So that pressure from that wind, we refer to that as velocity pressure. So if the wind is blowing at 20 miles an hour, the pressure in whatever measurement we want to use, PSI or atmospheres, or very frequently we use when we're measuring air pressure, especially in indoor air situations, we usually use a measurement called inches of water. In other words, the pressure against our face is the same thing as feeling the weight of 1 inch of water or 2 inches of water. So if a 20-mile wind blowing into our face, we might sense that as the equivalent pressure of 4 inches of water, and that's the way we would describe it. A 5-mile-an-hour wind would be lower. So now we have a combination of two kinds of pressure. We have pressure from the wind, which is velocity pressure, but even with that velocity pressure, we still have that ever-present static pressure. So we add those two together. So in the front of our face, what do we have pressing against in front of our face? We have the static pressure plus the velocity pressure. We call that total pressure. So the first basic formula is the total pressure is equal to the static pressure plus the velocity pressure. That's the total pressure. Okay, so how does velocity of air relate to velocity pressure? Okay, remember I mentioned that usually in ventilation systems, we refer to pressure by referring to the equivalent weight of water, height of water, right? So we have a formula that says the velocity is equal to 4,005 times the square root of the velocity pressure. So if the velocity pressure, and this formula is meant for indoor air systems and exhaust systems, so we always use measurements in inches of water. So if the velocity pressure is 2 inches of water, or 4 inches of water, the square root of the velocity pressure is 2 inches. It's 2, right? So that's 2 times 4,005. So we need in order to get 4 inches of pressure against our face, we need 2 times 4,000. We need almost 8,000 feet per minute of air blowing in our face. 4 inches of water, that's a lot of pressure, relative to compared to what it is for air. So this formula works because the 4,005 is meant to combine a bunch of different factors and work with the velocity pressure expressed as inches of water. Okay, not PSI. If you have PSI, you got to convert that into inches of water to use that formula. So that's our first formula. Total pressure is static pressure versus velocity pressure. And velocity pressure, we know we can exchange the velocity pressure for the actual velocity air. Faster air movement, the higher the velocity pressure. More the velocity pressure means the air is moving faster. Static pressure, okay, a fan creates negative pressure, suction, right, on one side, and it blows out the other side. We use that in order to change that static pressure into velocity pressure. We have a fan going, it starts to suck air, it's connected to ductwork. What's it going to do? It's going to start to suck air through that ductwork. So what velocity are we going to generate in that ductwork? It's going to depend on the horsepower of the motor, the amount of static pressure that we generate, the amount of friction in the ductwork as it goes through the ductwork, number of turns that contribute to the friction, and so on and so forth. So in industrial ventilation, we look at all those different properties, and we can figure out if I want 100 feet per minute from a 1-inch duct right here, we have formulas that'll help us figure out how big a fan that we need 100 feet away after it's made 7 turns. That's what we do when we design industrial ventilation systems. Why did I say 100 feet per minute right here? Because that's what we need to capture the contaminant to keep it away from the worker. It's not always going to be the same amount, right? It's going to depend on a lot of things. Among other things, it's going to depend on the type of contaminant that we're going to try and capture. Do you think that we need higher velocity? Let's say that we own a nail salon, and there's been a lot of controversy about nail salons and acetone and the other chemicals that they use. Do you think we need higher velocity to capture acetone that somebody's using on someone's fingers to take off a nail polish, or do we need a higher velocity to capture material that we're grinding out between bricks? Which one of those two do you think takes a higher velocity? Bricks, yeah, why is that? Because the bricks are big particles, right? When you grind them out, they're large particles. You need a lot of velocity to capture those particles. The acetone is just a vapor. So basically, if you can capture the air alone, then the vapor is going to come with it, right? It's a little bit lighter than air, so it'll drift up, it'll diffuse a little bit, but you don't need the same velocity as you need to pick up big particles of grit and concrete and so on and so forth. Okay, so how do we measure velocity pressure? We measure velocity pressure by putting a device into a piece of ductwork called a Pitot Tube. This is a Pitot Tube. And one of the properties of velocity pressure moving through ductwork is that it doesn't move through the ductwork uniformly. If you look at that, can you see that, by the way? Oh, I got to get that thing out of the way, make it a little easier, right? Okay. So you notice that cone over there? When air is moving through a ductwork like this, very, very, very slowly, it's called laminar flow. Laminar flow might look kind of like that area that we have on the right side where all the air is moving through the ductwork at the same speed. We don't really get that in ductwork. Air is moving through there very fast, relatively quickly, and there's eddies and turbulence and so on and so forth. So we get non-laminar flow. And what happens there is as the air is moving through there, the air that's close to the edges of the ductwork is affected by friction against the ductwork, so it's moving slower than the air in the middle of the ductwork. So when we talk about the average amount of air that's going through there, we can't just measure it in the middle or at the edge and so on and so forth. We actually have to have a device where we can go in there and measure it at different points so that we can average them. Okay, so that's what we do with a Pitot tube. And this Pitot tube, what this is doing is that there's a little opening over here, and air, as it's coming in here, it's blowing against this Pitot tube, and it's connected to a device that'll measure the pressure, a gauge that'll measure the pressure, something called a manometer, right? So if I blow air in here and I measure it over here, am I measuring static pressure or velocity pressure? If I blow air in here, right, if I put this into the ductwork and the air is flowing in here, right, it's blowing against this and it's going through this tube, coming out here, and I connect that to a manometer, am I measuring static pressure or velocity pressure?
Velocity pressure.
What's that? Velocity pressure. Yeah, that's a trick question. What about the static pressure? Static pressure is always present.
Yeah.
You're measuring total pressure.
Yeah.
Right? You're measuring the static pressure, which is there even when the air is not moving, and you're measuring the velocity pressure. So how do you adjust for that? Well, the way you adjust for that, there's tiny little holes on the side of this. Yeah, well, I'll pass it around, you'll see it. Tiny little holes. It's actually two tubes. It's one tube inside of another tube. And at the same time that you measure the air flowing into the tip here, total pressure, right, velocity and static pressure, you have these little holes on the side that, since the air is passing over them, you're only measuring the static pressure. So you can connect this to the other side of the manometer. So basically you're measuring the total pressure, and then put this on the other side of the manometer and you subtract the static pressure. So this hooked up in the right way on a manometer is going to give you the velocity pressure, but only because it's measuring both at the same time. A little tricky, right? So this is one of the basic devices for measuring velocity pressure. And once we know velocity pressure, what can we convert that into? We can convert that into the velocity inside that ductwork. So this is a primary measurement device for velocity. We're going to look at other ones that are a lot easier to use, but functionally this still is the primary device that you would use in measuring the real flow through ductwork. Now there is a cheat. One of the cheats that people use is that the velocity pressure, that's CL, that's called center line on that formula at the bottom. If you put this in there and measure the velocity pressure right in the middle of the ductwork, if you multiply it by 0.81, it's an approximation of the average velocity pressure throughout the ductwork to save a little bit of time. But if you really want to know what it is for sure, You have to measure it. You have to measure it in different spots. We're going to talk about how to do that in a second. The other formula that's important to us is Q is equal to V times A. Q is the volume of air flowing. V is the velocity of air, and A is the cross-sectional area. So if I have 1 square foot, if I have a square duct that is 12 inches by 12 inches, if I have 100 feet per minute of air flowing into that through that ductwork, I have 100 feet per minute times 1 square foot. 100 feet per minute times 1 square foot is 100 cubic feet per minute. So it's units work out, right? So now if you have a 1 by 1 duct and you have 300 feet per minute, it's 300 cubic feet per minute. Well, now how about if you have a 6-inch square duct, 6 inches by 6 inches by 6 inches? How much at 100 feet per minute, how much air do you have flowing through there?
Say that again?
You have a 6-inch by 6-inch duct, square duct, right?
Yeah.
And you have 100 feet per minute flowing into it. When it was 1 foot by 1 foot, 100 feet per minute, it was 100 cubic feet per minute. If it's 6 inches by 6 inches square duct, how many at 100 feet per minute of air flowing through it? What's the Q? What's the quantity of air in cubic feet per minute? What's the area now? What's the cross-sectional area, A? The velocity is still 100 feet per minute. The cross-sectional area is how much? Oh, wait a second. What units are we using? We got to change it to feet, right? So it's a half a foot times a half a foot is the size of that cross-sectional area, which is a quarter of a foot, right? So 100 feet per minute times a quarter of a foot square is 25 feet per minute. Okay, makes sense?
Yeah.
We're okay with that? And the same thing, same deal. If I have a 12-inch duct and I have 100 feet per minute going into that duct, well, that's not a square foot, a 12-inch round duct, right? How do we figure out what the actual cross-sectional area? It's pi times the radius squared, right? So 1 square foot, a 12-inch duct, the air cross-sectional area is, well, it's 6 inches is the radius, but we have to convert that into feet. So it's half a foot. So it's half a foot times half a foot squared, a quarter of a foot times 3.14, right? So quarter, it's like about maybe 0.8 cubic feet, right? So square feet. So the area, the velocity 100 times the 0.8 would make that about 75 or 80 feet per minute. So that's the conversion. So if I have something that will supply if I have something that'll supply a fan that will supply 100 cubic feet per minute, 100 cubic feet per minute, but I want the airflow in the ductwork to be high. I want that 100 cubic feet per minute, but I want high velocity. What do I have to modify to make sure I get high velocity out of that 100 cubic feet per minute? I have to make the cross-sectional area smaller so that the velocity is higher. If I increase the cross-sectional area, what happens to the velocity for the same amount of air that I'm moving? It slows down, right? Right. So one's got to go up, and V and A, one of them's got to go up when the other one goes down. You know what? If you have the same amount of air that you're moving. Okay, so here's an example. This is air being drawn into a laboratory hood with an opening of 12 inches by 24 inches. If the average face velocity, if this is the opening of the hood, that's the average velocity that's going into this hood. If the average face velocity is 200 feet per minute, 200 feet per minute, what amount of air are we moving? Well, the volume of air, the velocity air is 200 feet per minute. The cross-sectional area is 2 square feet, 1 foot by 2 foot, right? So we're moving 400 feet per minute, cubic feet per minute of air. Okay, so let's take a look at a basic ventilation system. Here's a basic ventilation system. Basic ventilation system like this one, we have a hood at one end. The hood is the device that you design to capture the contaminant. In a laboratory hood, you make a big box with a screen, with a plexiglass screen. You can move up and down. And as you move that up, what happens to the velocity air that's being pulled in? It's going down. The face velocity is going down because the opening is bigger, So for the same size fan, you got less air getting pulled in. So you pull the plexiglass down, what happens to the air velocity of the face velocity of the air moving into that hood? The cross-sectional area is getting smaller. So with the same size fan, the air velocity getting pulled in is faster. So if you have a very toxic material, what do you do with that plexiglass hood? You keep it down low. So you get a very high velocity pulling air in, right? As a matter of fact, most lab hoods have markings on them, where those markings tell you that the person that calibrated that hood tells you when that sash, that when that plexiglass screen is down at this level, that you're getting 100 feet per minute of air velocity being pulled in through that opening. Or another marking that's lower might say 200 feet per minute. So you know what level air is being pulled into that. So you know what level you need to protect yourself from one, depending on how dangerous the material is that you have inside the hood, right? So this is basically how a hood would operate. A hood for a welding operation is not going to look the same as a hood for a laboratory. Laboratory, you put it against the wall, the chemist goes over, he does his work inside the hood. A welder, he's got to be moving around. He's got to move to his work. So the type of hood a welder uses is a flexible hood, a cylindrical hood that's flexible, that's on a device that he can aim, and he can bring that over and put it behind his work. So as he's welding, it can get sucked into the hood and exhausted somewhere else or filtered, right? So that hood's going to look up. So the basic beginning of an exhaust system is that hood. It's got to be designed for the work that it's got to do. In a wood shop, it's a hood that's underneath the blade of the table saw. On the grinding device that the guy's grinding mortar out with, his grinder actually has a shroud on it that covers the grinding part, protects his hands, as well as it's connected to a vacuum system, so that as he's grinding these particles, those particles are shooting into that hood and are getting sucked away from him as well. So it's going to be designed. There's many different designs, and the American Congress of Government Industrial Hygienists has a whole manual on the proper design of hoods for many different kinds of operations. Now that you got that crap being pulled, crap is a technical term for dangerous materials in industrial hygiene. Now you got that crap being pulled into this hood. We know that it's got to be pulled in at different velocities. First, you need to get the air moving at the point where you're collecting it fast enough to grab it before it can get to the worker. That velocity is called the capture velocity. So for our acetone in our nail salon, we might only need a capture velocity of 50 feet per minute, right? That's how fast we might have to move. But that grinder might need a capture velocity of 300 feet per minute. Our lab hood might be 200 feet per minute in order to that's capture velocity. Now, once that nasty stuff is inside the ductwork, right, and you've captured it, you got to get it out of you don't want it settling out in the ductwork or sitting in the ductwork. So now inside the ductwork, you have to figure out how fast do you need to move air through the ductwork in order to keep that stuff from dropping out. So what happens if the air is moving too slow? Those grinding particles are going to drop out inside that ductwork and accumulate and clog up that ductwork. What's going to happen if the wood shop, the sawdust is going to settle out and clog up the ductwork and the hood. And so you need something that's going to keep that stuff moving through the system. That's called transport velocity. So now you got capture velocity and you have transport velocity. So all that nasty stuff, if you don't like your neighbors, you could just send that out through your fan and just point it at at the next building and so on and so forth. But in most cases, that's probably illegal, right? So you need to capture that in most situations, or you might wind up in trouble with the Department of Air Resources. So what do you do with that? You need some sort of scrubber or air cleaner device. If it's sawdust, it's probably just a basic filter, media filter of some kind. If it's cooking odors that you're getting complaints about, it might be big screens with activated charcoal in them to remove the cooking odors. If it's VOC, it's probably activated charcoal, and so on and so forth. If it's particulate material, it might be media filters, like filters you might have in an air conditioning system, or it might even be a scrubber, like a little cooling tower, like something that sprays water through the air and scrubs those particles out of the air before it gets sent outside. So a lot of times you'll put that before the fan. Why will you put it before the fan? Because fan costs a lot of money. You don't want to destroy your fan. So if the material is caustic or acidic, if it's abrasive, like coarse materials, you don't want it damaging fan blades. So a lot of times that'll be before the fan. And then the fan, once you get to the fan, now you got to get it outside the building. So the fan goes somewhere else, goes up, maybe goes up outside of the building, and it goes to a stack of some kind, like a small chimney or a stack or something like that. A lot of times there has to be a certain distance above the building, so you don't want that stuff accumulating on the roof if you're exhausting it outside, or getting sucked into a fresh air intake or something like that, if you're not using that kind of thing. So again, typical, simple, local exhaust system, a hood of some kind, ductwork, an air cleaner, more ductwork, the fan, and the stack. Okay, there's a few pictures. There's my basement fan. Here's some filters that you see on the bottom there. There's a small spray paint booth, and there's a million different kinds of hardware and devices for this. Okay, we'll just get some simple ones. Now, how do you measure the airflow, the capture ventilation, and so on and so forth? We're going to look at some instruments here. The simplest of these in this picture, I don't have them here, they're smoke tubes. They're just tubes that 40 years ago, if you were an air conditioning mechanic and you were checking, like exhaust on a boiler or something like that, or you were checking to see airflow, you just take the cigarette out of your mouth and blow into it and see what happened. Nowadays, you don't do that anymore. Now you use tubes that generate a non-toxic gas. In fact, they're not that non-toxic, but they produce a smoke, a safe smoke, relatively safe smoke. Static chloride or fuming sulfuric acid. It condenses moisture in the air into tiny particles. So you see and you can track the visual, you can visualize the air movement using that. That's qualitative though, right? That's okay if you just want to get a rough idea of whether something's working or not. But if you really want to measure it, you have to use instrumentation. And we have a bunch of this here. Okay, so a couple of them that we have are anemometers. Anemometers means it measures the airspeed. This one that's on the right here is a rotating vane anemometer. You see there's a little fan in there, there's a vane in there. When that spins, you can actually measure the airflow. We have one of those here. We're going to be using it. Okay, and on the right side here, that's a manometer. It has the two little ports in it. There's a pressure difference in the air. You can see it on that gauge. In other words, measuring the pressure difference between one location and another location. There's other ones that are called, this one, the one on the right here is a inclined manometer. And what that one does is that, remember we're measuring in inches of water? It literally, you connect your Pitot tube to it and you actually watch, there's a red fluid in there which is substituting for water. You can watch to see how much it pushes up that column of water. So you can judge what the velocity pressure is. From the velocity pressure, you measure the velocity. Okay, here's a picture of our Pitot tube. There's the two little holes that are in the side, and you can see that there are actually really two tubes there. One to measure static pressure, the other one to measure total pressure, which then we can find the difference between them, and we know the velocity of the air that's moving through them. In this setup, what are we doing here? Well, this first one is coming off the side of that Pitot tube. It's coming off the side. The one that's coming off the side is measuring the stuff on the holes around the outside of this thing. That's static pressure. On the second one there, it's coming off the top of the Pitot tube, which is connected to the front of this tube, right? So it's measuring the total pressure. So now if I connect the top of this to one end of the manometer, either liquid that gets pushed up or down, or that spring-loaded gauge, doesn't matter which one. If you connect one side to this to one side and this to the other side, you actually can have one side pushing on one end, the other side pushing on the other, and the difference between the two is the velocity pressure, which is usually really what you're after. Okay, and here's a typical ductwork system. And what we've done here is the static pressure outside of the hood is 0. right? So the static pressure outside of the hood is 0. It's just air pressure, right? Now we need to know what amount of static pressure do we need at the fan in order to get that first measurement there. Static pressure is equal to 1.2 inches. That point over there is called the hood static pressure. The manufacturer of the hood tells you that in order to get a certain amount of velocity, capture velocity from that hood, you need at that point, right at the back of that hood, you need a certain amount of suction, right? So in this case, you need 1.2 inches of water. That's the amount of suction that you need. But now the fan is all the way down at the other end of the plant. Got to go through a bunch of duct work, a bunch of turns, got to go through an air cleaner and so on and so forth. So you literally have to figure out how much energy am I losing? How much static pressure do I have to add to that 1.2 inches so that I really get 1.2 inches there? If I had only 1.2 inches at the fan, you see at the fan it says -3 inches, 3 inches of water suction pressure, right? If I only had 1.2 inches there, I would have almost no static pressure at the hood because it would be lost to all the turns. So I need to know how much static pressure do I need at that fan in order to have 1.2 inches of static pressure at the back of that hood. And what we do is we calculate what the velocity is that we need for the capture, that velocity that we need, and what size of the ductwork, capture what that velocity is, and we have tables that'll help us calculate how much static pressure loss, how much energy we're losing to friction and other issues on turns and so on and so forth as we go through this ductwork and the air cleaner and so on and so forth. So in the end, we find that if we have 3 inches of static pressure at that fan, we're going to have 2.6 inches after the filter. We're going to have 1.6 inches before the filter, and we're going to have 1.2 inches where we need it. So part of designing this whole thing is figuring out how to get that amount of static pressure that you need to make that fan work properly and to make sure you have the velocity that you need. Okay, so I'm going to go over this once we get up the equipment. We're going to measure the velocity pressure in a piece of ductwork, and we're also going to try and figure out if we can't find somewhere to measure some static pressure. When we're measuring the velocity pressure for a hood, the opening is a rectangle, right? You pull the sash up. If it's at this level, the opening is a rectangle. But there's going to be eddy currents. Not always going to be the same amount of velocity across the whole hood. So if I measure it, if I measure that hood face like this, if I measure it here, I'm going to get a different velocity than if I measure it here, or measure it here, or measure it here. So we need an average. So what you do is you break this up, like I'll break this up into 2 rows and 4 columns. So I have 8 boxes here, right? So if this were 4 foot by 2 foot, I would have 4 a box that's a box. All these boxes are 1 foot square, right? So it could be any. It doesn't have to be that way, but that's one way you might break it up. So what you're going to do is you're going to take each one of these 1 square foot boxes. You're going to find the middle of it and take a reading there, and the next box, and the next box, and the next box, and the next box. And you're going to take those 8 readings and average them, and that's what you're going to call the face velocity for that lab hood, right? For the opening that high. So now if you lowered it to 1 foot, now your boxes might be 6 inches by 1 foot, 6 inches by 1 foot, 6 inches. So you're going to take it 3 inches high and 6 inches across, and the next one, and the next one, and the next one, and average those readings that you take, right? And you'll take enough, you'll divide it into enough boxes to get a decent estimate of the overall flow velocity, face velocity for the hood. In this case, we've got 16 points and so on. If you have a round duct gets a little bit more complicated. You can measure, this actually will fit into a ductwork, and you can use this to measure the velocity pressure in the middle of the ductwork or at the top of the ductwork. Let me get this. Right, so you got a hole in there, it comes in here. So you can measure it at the middle, you can measure it up here, you can measure it up here. Now, but you want to measure it, each measurement, you want it to represent a certain area, and you want all the areas to be the same. So you don't want one measurement to represent 50% of the area, And another measurement that you're going to weight the same way, you measure only 10% of the area. You want all your measurements to represent the same area, just like you did with the hood. Problem is, with a round duct, is that you can't just say, I'm going to go down halfway, and that's going to be half the area. That doesn't work that way, because if I go from 3 inches in diameter to 6 inches in diameter, I don't have twice the area, I have 4 times the area. So if you look at these locations, see little pin, these little circles where you're measuring on the left-hand side, where you're gonna place your Pitot tube in order to take a measurement, you'll find that as you get to the center, the points where you're gonna take the measurement are spaced further apart. Why are they spaced further apart? Because they have to be spaced further apart for each one of those cylinders to represent the same cross-sectional area as the next one. On the outside, that little sliver on the outside measures the same amount. Let me see if I can't do this. This area in here, right? That whole thing is the same cross-sectional area as this area out here, right? Because it's on the outside diameter of the ductwork. Is the same area as the area in here, and so on. That's why you're taking so many of those readings. Often you'll take 10 readings. We're going to try and do it with only 6 readings. Okay. Okay, so I want to stop here. Well, let me just go through the rest of these very quickly. Okay, you can go through these PowerPoints on your own. Here's an example of a ductwork. Look at these 2 pieces of ductwork. What's the difference between the 2 of these? They're the same size. Let's say they're the same size. They're both 1 inch by, let's say they're both a 1 foot by 2 foot opening, right? The length and the width is both 1 by 2. Which of these 2, 6 inches in front of it, you think will give you more air velocity? Yeah, flange duct. Why the flange duct? The flange duct, because when we have an unflanged duct, it's going to pull air from all directions, from the front and around the sides. So the flange discourages it from pulling air from behind the ductwork. So the same amount of static pressure here will give you more velocity at the same distance in front of the ductwork. So we're going to see if I can't find some cardboard, and we'll set up a little flange duct here to see if we can't measure that. Okay, so we're going to do now, we're going to take a quick break. We're going to set some equipment up, get this stuff out, and see if we can't start taking some measurements. And I'm going to show you very quickly. Whoops, escape. Let me hand these out. Okay, so here's our exercise. There, just grab 2 pages, grab the top 2, pass the rest on. And here is somewhere to record information. And what do we have there? Okay, so what we're going to do is we're going to take round ductwork, and we're going to get that, make the fan start running, and then we're going to measure the velocity pressure at 6 locations. Well, what are going to be the 6 locations that we're going to measure it at? There's another chart. There's a chart there, which will tell you that if you have 6-inch ductwork, you have to measure the point you're going to measure for 6-inch ductwork, if you're going to take 6 readings, 3 on one side, 3 on the other, is 0.32 inches in, 0.135, 0.32 up. Oh, these are the percentages of the way through the ductwork that you're going to have to go. So we're going to have to figure out what that percentage is for 6 inches, right? So 0.032 of 6 inches, 0.0135, and we'll figure that out and we'll get those velocity readings. Then what we're going to do is okay, we'll take those. We will then set up our exhaust hood, and we're going to take readings on our exhaust hood from various locations. Okay, so let me get to our exercise there. So this is where you're going to record your velocities for the duct using the Pitot tube. Then we're gonna measure a hood, 2 different hoods. I'm going to give you these numbers as if you took them yourself, but you're going to use the instrument on the front of this hood so you see how the instruments work. Okay, and then we're going to use the barometer to measure the amount of air that's coming out of a diffuser. We can't get here because of the light, but we might be able to sneak into those. There's one in the hallway we can get to very easily. So let's get the instrument out and let's get started. Okay, so. Okay, so I got tape all over these things, and there's a reason for the tape all over these things. The reason is that it's easy to get cut with this stuff.
It's easy to what?
Get cut.
Oh.
Right, so very sharp edges. And mechanics, they wear Kevlar gloves for the most part when they're working with this stuff. Unfortunately, I don't have them here, so I'm gonna take my chances. You know, maybe I can just squeeze it in there.
Sure.
And then you can know which side is going on. Yeah, there's the arrow. The arrow's going that way. Good. Okay, I need somebody to tape this for me. I'm not gonna try and shove this in there. So the tape is on the floor.
Tape.
There it is, on the floor there. Okay. Yeah, start by pulling that, get it started, pull a big piece out.
Your name.
Okay, pretty close. Careful. Okay, that's good enough. That's good enough, I think. Okay. Yeah, go around it. You want to get it on the intersection between the two of them so that it stays together. In other words, cover the white also. Yeah, you can keep going. Don't worry about it. It's cheap. Go down to the white.
Go to the white, okay.
Yeah. Yeah, you want it to join together. Yeah.
Is that okay?
Yeah, that's good. Yeah, cover the whole thing. Yeah, there you go.
Is it
Or
good?
for
Good. Cover the whole Bring up a little bit, yeah, you good?
It's not straight though.
Yeah.
That's okay. Doesn't matter. Okay, that's good. Tear it off. It'll rip. Good. Okay, good. All right, let's get the extension cord. Where's the hole? There's a hole.
There's a hole here.
Yep, there is a hole there. Okay, let's get the extension cord and plug this thing in.
What's the extension cord?
Right there.
This?
That's it. Okay, so first lesson about industrial ventilation systems, and you know this from your vacuum cleaner. Okay, good. Okay. How far away can you feel that? You feel that over there? I can see the window. how close do you have to get to this to feel the air moving? You gotta get damn close, right? These systems by nature are inefficient that way. That it's pulling air in from all these different sides. So you lose a lot of the energy from this system. A lot of the velocity is lost to, you want to capture the energy, right? So this might be only 10 feet per minute. This might be 20 feet per minute. This might be 100. You get very close to this to get to the velocity that you need to capture the material that you need to capture. So depending on what material is, you might need a lot of air moving through this in order to capture the dense part of the heavy part of it. So we're going to want to start to measure this. So it's how we're going to measure this. We don't have any fluid in there. One way to measure it is to use this device, which is a manometer. Well, all the connectors are gone. I'm going to hold it there for a second. It's going to fall over. So we would normally connect this Pitot tube to this manometer, and we would see one side to capture the total pressure, the other side capture the velocity pressure, and we would see the water, the inches of water that were displaced. Well, we're going to use something else to do that now. And there it is. Let's try that one. Okay. Anybody got a pocket knife?
Sorry?
Pocket knife? Anybody? Nobody.
Okay.
No. Nobody was ever a Boy Scout here. You have a pocket knife? Seriously? How about a scissors? Anybody got a scissors? Nobody carried a pocket knife. Not even like I can't believe that. I normally have a Swiss Army knife on me, but I don't have it. Nobody here fishes or goes camping and stuff like that.
I'm ready to do. What are you trying to do?
I want to cut this in half. Yes. Yeah, we got scissors, anything. Anybody got the strong teeth, doesn't mind biting a rubber? You got something? You have something there? Keys? Maybe somebody out there has got a pair of scissors. Yeah, let me cut it. I need 2 tubes. And that's the right size. That's the only one that's really the right size. There might be somebody out there with a pair of scissors. Maybe in the other office. Somebody with a pair of scissors. Well, how about next in the cafeteria? Yeah, we managed to get a cut with only a minor injury. No, a butter knife. We got to use a butter knife. calibrated, it's just zero. They're coming out of the house. Okay. Here. I'm gonna put this in here and see if we can do something. What are we reading right now? Okay, what is that? What am I reading? What am I connecting? That's what's on the other end. My Pitot Tube. I'm connecting here, which is connected to this, which is, what is that? No pressure? Oh, that's a no pressure. What is it again? 0.30. Okay, so now, what if I were to connect this here? And I'm connected to the other side. It's connected with little pinholes over here. What am I reading now? 0.42. Okay, 0.42. What pressure am I reading now? Nothing. Right. Okay, so now, 0.42. Yeah, the first one was 0.2 there, the second one was 0.42. Okay, what am I reading now? 0.15. 0.14. So the difference between those two pressures, why is that happening? Because I'm taking the total pressure, subtracting the static pressure. Right? So now, we're going to take 6 readings. Okay. Okay, now, normally, what I would do is, remember, you see that chart that I have down? That's the 6-inch ductwork, that the first reading has to be 0.035 times 6 inches, 0.35, whatever it is. Write that amount in. Really what you should be doing is converting that into inches and then marking this. You may notice that there are markings on here from a previous reading. Marking this so that you know that at each point, you know that the first reading at the top should only be a little bit down, right? That's close to the top. The second reading will refer to that. Right? I'm not going to bother with that. I'm just going to do 6 readings, but I think it's approximately right. But really, we should be doing it right. We should be doing it according to the percentages of 6 inches that are in that chart. Okay. Right? Because we want equal area surface. Right? So okay, let's take the first one. What do you read there? 0.08. Okay, why is it so low? Because I'm close to the edge and the friction is slowing it down. So I'm going to take another one. 0.10. Okay, get higher. 0.09. Okay, well, it's okay. This happened. Yes. 0.10. Okay, yes. 0.10. 0.111. Okay. 0.115. 0.17. 0.22. 0.28. 0.29. Okay, let's try it again. I'm going to stop and stretch. Okay. Okay. All right. So what I want to do is make this one. Hopefully, I wish this was straight up and down. I didn't do that. Okay. Good. Okay. So I'm going to try to get this straight on. Okay. First reading. 0.10. Second. 0.011. 0.16. 0.17. 0.22. 0.26. That's probably should be low again. It's really hard. 0.22. Okay, right. So that's just reading. We'll just use those readings. Okay. I would have expected that the bottom would have been low again because we'll do it again. Yeah. We'll do it again. Okay. Back on bottom. Go to the top. Yeah. Okay. So now it's 0.12. Okay, that's more like it. Okay. 0.2. 0.26. Yeah, we'll get away from the sun. 0.27. That's the other one.
0.31. 0.18. 0.14.
Okay, let's use those. Those seem most realistic. Okay, so that's, what is that? That's velocity pressure. Right? Everybody understand it? We didn't measure the velocity. We measured the velocity pressure. What are the units? Inches of water pressure, inches of water. We're going to take those numbers and average them. Some kind of calculator, take calculator, average those numbers. No, average. Add them all up, divide by 6. Yeah, average. Add them all up, divide by 6. That's going to be your average velocity pressure. Once we get that, we're going to convert that. Make sure you use the last readings that we've done. Everybody use the same readings.
0.213.
That's the average. The average velocity, inches of water, 0.213 inches of water. Now, what do we do to convert that into velocity, feet per minute? Remember that formula? Velocity is equal to 4,005 times the square root of the velocity pressure. What's the square root of 0.213 or whatever it was? What's the square root of that?
0.46.
Okay, 0.46 times 4,005.
1,848.
1,848. So the velocity of air moving through here is 1,400 and whatever it was. 1,800 feet per minute. The velocity of air moving through here is approximately 1,800 feet per minute. Let's figure out what the volume is right here. I'll wait for you guys to catch up.
So it's 1848.
Okay, I'm going to call it 1,800. Make it simple.
Okay.
1,800 feet per minute. What's the cross-sectional area of a 6-inch duct?
Pi r squared.
Pi r squared, but you got to change it into feet.
16 feet, right?
Right, so it's 6 inches, so half a foot is a quarter of a foot is the radius. So 0.25 times 0.25 times 3.14. Right, cross-sectional area, pi r squared. 3.14.
0.9.
How much? 0.19.
3 from 1.25. Yeah, and 0.25.
Okay, so if we want to know what the volume of air moving through here is, Q is equal to the cross-sectional area times the velocity.
What was
The
that?
cross-sectional area was 0.19 whatever,
196.
okay, times the velocity, which was 1,800.
Yeah.
What's that come out to?
That comes out to 3.25.
3.5, okay. This fan is rated for,
Yeah. So together.
this fan is rated for about 350 cubic feet per minute. Hello?
So, 1 second. So, if we multiply the cross-sectional area with the velocity, what do we get?
The velocity Q, the volume, is equal to the velocity times the cross-sectional area.
Yeah.
So you got A times V.
8 is 100, V 0.193.
Okay, what is it up to?
353.25.
Okay, 300, this fan is rated, I think it's rated by the 300 or 400 cubic feet per minute. You hit the nail right on the head, first shot out. Flow rate was 1,800 feet per minute.
This is the echo. So what do you just calculate now?
So what do we just figure out? What's it?
What do you just calculate? What do you do the echo?
Q is the
Q
one.
is the cubic feet per minute, the volume of air.
Okay, so the Q is V times A.
Right. Okay, so that actually works, right? Okay, so let's take a look at ways of doing other measurements as well. Let me check. Let me do one more thing first.
125. Right, yeah. Yeah. That's how we got the area. Yeah. That's how we got the money. That's how we got it. Yeah. We're trying to get area of the sample, right? And then actually you're looking for more saturation.
Okay.
Sorry, flashback.
Yeah.
Area is
No, not the volume, the area is pi r squared.
It's one set area. You know, it's one line is one set area, right?
Hey guys, look up for a second. Okay, so here is our ductwork, right? So we determined that the velocity in the ductwork was 1,800 feet per minute. That's how fast it was moving, right? Feet per minute. The area, the cross-sectional area is the area of the face of the ductwork. That area is equal to pi times r squared, but it's got to be in feet, right? The area is 3.14 pi times the radius is 1/4 of a foot, 1/4 squared, right? So 0.25 times 0.25 times 3.14, that area came out to be 0.19. So now 1,800, which is the velocity, feet per minute, times the cross-sectional area, 0.19 feet squared, right? Multiply those out, we got 350, what is it, cubic feet per minute, right? That's our Q. So this is Q, this is V, and this is the cross-sectional area. So Q is equal to V times A. Okay, so let's take another measurement. Now, one of the things that we're interested in is the capture velocity. We need to know how far that worker has to be from the front of this hood in order to be protected. So this is called a vane anemometer. It's got a little vane in it. It's got a little propeller in it. Right? If you hold this against the front of, set 30 right now. If you hold this against the front of the hood, that's a hood. What's the big right now?
2.99 feet per minute.
Okay, right now move it back 6 inches. 6, that's 6 inches. Keep going. There you go. Now you're about 6 inches. What's your width now?
617 feet per minute. 313 feet per minute. 168 feet per minute.
At 6 inches, it's reading roughly. Well, we need a ruler. Show fancy pencils. Okay. Actually, you can use the paper. Right? The paper's 11 inches. You can fold it in half. It's going to be roughly 6. Okay. Now hold it exactly 3 inches. Right up front, 3 inches. Okay. You don't want to hold it right against it. Hold it exactly. You can use the ruler for this one. Hold it exactly 3 inches from the front of the hood, right in the middle. Now the only trouble is that you got to take your other hand away. Okay? Good. Okay, what are we reading? 3 inches.
266 feet per minute.
Okay, good. Write that down. 266. Before it changes, you got to find out what it is. Okay. Okay, so now try to get 6 inches away from the base of the rock. Look over against the base of the rock. Yeah, 6 inches. No, you gotta have that look over against the hood. Yeah, there you go. It's 1 6 inches. Okay, good. And then the other hand away in the center. Whatever it is now.
116.
160
So that's
feet per
accurate.
minute.
Oh, that's decreases.
Oh, decreasing. So that you get further and further away. Okay, now try it again. Try it again, 12 inches. Try it again, 12 inches away. 12 inches away. Okay, now try 9 inches. 88. All right, so what happens? So if we need 100 feet per minute to protect this worker, if we need 100 feet per minute to capture the contaminant, this worker can't be working 9 inches away from the base of this hood. He's got to be within 6 inches of the base of this hood. That's capture velocity. We need enough velocity. So if we need him to work a foot away from here, he can't get closer than a foot. What do we have to do to make this work? If he's got to be working a foot away from this hood, we need 100 feet per minute. We need a bigger fan. We need more velocity, more static pressure, more velocity in order to get it so he can be further away. And we designed this. This is what we do with the ventilation. We actually designed this. So this is a vane anemometer. This is a thermal anemometer. It's got a little heating element in the end of it. And what happens is it measures the air velocity by measuring the amount of heat it loses as the air passes through it. Okay, good work. Good try. Yeah, just so you guys, no, concentrate. Yeah. Yeah, like even if you just that. You're never going to be measuring right at the end of it. And all the work is going to take place in the front of it. That's called a thermal anemometer. So the first one was a vane anemometer. This is thermal heat. So it's got a little heat element. It's got a little resistor, a little heating element. And the rate at which you pull the air from the person is pulling heat away. So hold this out about 6 inches. Yes, so reading basically the same thing you did with the thermometer as we read with the vane.
No, that was strange.
And you know why that might be? The reason it might be happening is because you've got that big fist of yours and that big vein stuck in front of our duct work. So you are modifying the performance of this duct with those giant bits. With this one, you're able to take the reading without this one down here, right? Okay, so do another measure of base velocity on a hood. Which of these two instruments would be better? It would be better to use this one. So you have to extend. So you can extend. So you can make the base velocity without standing in front of it. Speed your reading. So this has a lot of applications in areas where you don't want to do testing in front. You want to put it in line. So this is like okay. And that's okay, so that's basically it. If you guys want to pass the instruments around, I just want to give you one more set of numbers. And since we don't have a lab hood here, I got one more thing I want to tell you. Okay. You know, something you can cover with any of that hood here. Okay, what's the velocity pressure in here?
Zero.
Zero. Don't air me through there. What happens to the static pressure? It goes higher. Static pressure goes higher. Well, you know that energy. So the static pressure is potential energy, right? It's waiting there to do some work. And when you take that off, it becomes kinetic energy. So the static pressure goes down because it's exchanged for velocity pressure. Okay, good.
So can we say that static pressure is abundant in indoor areas?
Is static pressure? You want to? Let me turn the fan off so I can talk. So let's talk about this. This room that we're in here, are we under a positive static pressure or a negative static pressure relative to outside? Any other opinions? No. Why is it positive? Why are we under a positive pressure relative to outside? What's being pushed into this room? Air is being pushed in here, right? So this room's under positive pressure. The ceiling is connected to the fan, in the mechanical room. It's sucking air into the ceiling's a negative pressure. So that's what gets the air moving through here. The fan's pushing it in here under positive pressure. It's getting pulled back up into the ceiling under negative pressure. Okay, so the only other thing that we have here is that in that sheet, we are supposed to measure, on that sheet, we're supposed to measure the face values of a hood. I'm going to give you some numbers to use there now. Hang on, just let me give you some numbers first. Okay, let me find this now. Let me just get this out. I want to make sure you have these numbers to play with. Okay, so here, you have 2 4-point readings and 2-point readings. I'm going to give you some, so hood 1, I'm going to call this, I'm going to make these numbers up. We would actually measure this if we had a hood here, right? I'm going to call this 90, 120, 100, and 105. Okay, so you can calculate based on this what the cross-sectional area of this hood is, right? You can calculate what the volume of air going through here is. But in order to calculate the volume of air, you got to get the average velocity first, right? Okay, and an 8-point, I'll give you another one. This is another hood, 210, 300, 250, 205, 210, 220, 280, and 190. Okay, and calculate the readings for that one as well. Okay, what are you going to calculate? For each one of these, you're going to calculate the velocity. What's the velocity? It's just the average velocity. These are all feet per minute. It's just the average velocity as if we took the thermal anemometer or the vane anemometer and that's 90. This one's 90. Vane anemometer held it in front. That's what the reading we got. So you want to calculate the average velocity. And now that you know the average velocity, calculate the square footage that you have. This is 4 foot by 1.5 foot. So 4 times 1.5 is going to give you the cross-sectional area. So you got your area. And now you can calculate Q, the cubic feet per minute, which is the velocity calculated times the cross-sectional area. And that's in cubic feet per minute. And the same thing down here. You calculate your average velocity, right? And then calculate your cross-sectional area. This one is 4 foot by 1 foot, so that's 4 square feet, right? And then you calculate Q, V times A.
Thank you.
Okay?
Okay.
Good. So that's it. Let's call it a night. Let's